recent research on universal parity quantum computing. And in the scope of that, I will first of all go into what the LHZ architecture is. This forms the basis of this whole project. Then I will elaborate on how we found the universal gate sets in that architecture, present applications of it. I will also go into how to encode and decode quantum states in the LHZ or parity architecture, and briefly go into its fault tolerance property, and finally come to a conclusion. Please also, during my presentation, feel free to interrupt and ask questions at any time. I think this can be very helpful in terms of understanding.
Okay.
All right. So what is the LHZ architecture? So let's start with the parity transformation, which was basically invented by my supervisor Wolfgang Lechner and his co-workers Philipp Hauke and Peter Soller in 2015. And the main purpose at that time was to map optimization problems to a quantum computer. Many NP-hard optimization problems can be formulated as Ising spin glasses, which have the Hamiltonian shown here, or at least the Hamiltonian of a similar form. And the problem with this Hamiltonian is that it requires a high qubit connectivity. So for example, if all these Jij coefficients are non-zero, you need a device with an all-to-all connectivity. And this is something that is very hard to tackle on state-of-the-art quantum computers, and that's what Wolfgang Lechner and others looked for a solution for. And what they did for their solution, they did the so-called parity mapping. And for that parity mapping, they did now not represent each logical qubit as itself on the physical quantum device, but they mapped the parity of pairs of logical qubits to one physical qubit. So in this picture here, the green qubits would correspond to the physical qubits, whereas the blue qubits correspond to logical qubits. And if they are parallelly aligned along the z-axis, they are assigned eigenvalue 1, which corresponds to a 1 in this labeling here. And if they are anti-parallelly aligned, they are assigned eigenvalue -1, which corresponds to a 0 in this labeling here. I'm not entirely sure why they labeled it with 1 and 0 here, but maybe I could also change that in future. But yeah. So what this leaves us with is this Hamiltonian here. However, the problem is we had n degrees of freedom, and now if we use the physical qubits, we have n times n minus 1 over 2, which is equal to k in this context, degrees of freedom. This is because now every connection between two qubits, which is of course the binomial coefficient n2, this enlarges now the number of degrees of freedom. And so what's nice now is that we only have those single qubit terms and no longer this long range connectivity. However, in order to reduce the number of degrees of freedom again, such that we have the same number of degrees of freedom as before, we need to introduce k minus n constraints. And one difficulty when setting this transformation up is how to find these constraints and to identify actually what these constraints are. And it turns out that these constraints turn out to be 3 or 4 qubit terms like they are displayed here, and that they can be implemented very locally. So they do not require long range connectivity. All right, so let's now go a bit into how these constraints work. And these constraints are basically formed from conditions on so-called closed loops. A closed loop on a logical graph is a set of edges that form a closed loop. So for example, here, if we have logical qubits 1, 2, 3, the edges to which physical qubits correspond are 1, 2, 2, 3, and 1, 3. They form a closed loop. And on this closed loop, we can now have the following conditions. So if you look at the right-hand side of this table, you see the configuration of parity qubits. 1 again means that the qubits are antiparallel. Means that they are parallelly aligned, and 0 means that the qubits are antiparallelly aligned. So, for example, here we say we have 1, 2 are parallelly aligned, same for 1, 3, same for 1, 2, which means, of course, that all are parallelly aligned. And this is true for the two cases if all spins are up or all spins are down. So there is a global spin flip degeneracy, but this does not matter because this is anywhere lifted if there would be local fields on the qubits. Another possibility is that 1, 2 are parallelly aligned and the other two anti-parallelly, which sorry, the other way around. I always confused it. So 1, 3 are anti-parallelly aligned. So 1 is 0, 3 is 1. Same for 2, 3. 2 is 0, 3 is 1, and 1 and 2 are aligned the same way. So they are both in state 0. However, there can now be cases that contradict each other. So for example, the lowest one here in the physical mapping says that qubits 1 and 2 are parallelly aligned, also 1 and 3, which would already say that all of the qubits have to be in the same state. However, that 2 and 3 are anti-parallelly aligned contradicts this statement, and therefore this is a non-valid configuration. And in order to establish these constraints now, we have to prohibit these contradicting states. And basically that this is fulfilled. The condition is that in each such closed loops, the number of spin down qubits, so the number of physical qubits that imply an anti-parallelly alignment, this number of configurations has to be an even number or 0. So either there are 2 physical qubits specifying a anti-parallel alignment, or 4 or 6, or none. Is there any questions on that so far?
No, we are good. Thank you.
Great. So then let me continue. We now need to bring these constraints somehow to the chip. And this is also one of the main findings in this paper from 2015, that these constraints can be laid out in local interactions on a 2-dimensional quantum chip. And when we look into how we do that, let's now, for this Ising model here, construct these closed loops. So let's start with parity qubit 2, 3, and place this on the very bottom line of the chip. Then we continue on this loop and add parity qubit 1, 3 on the next line. So this variable s here indicates the difference between the logical indices involved in the physical qubit. So for example, here we have 2, 3. 3 minus 2 is 1, therefore we have s equals 1. Here we have 3 minus 1 equals 2, so we have S equals 2 and so on. Right, so we have now placed this parity qubit 1, 3. Let's again continue the loop. This goes now on to qubit 4, so we involve 1, 4. We can place that here. And what is missing now is a 2, 4. So we place that also here. And you can now see we can verify that this is a closed loop. That it is a closed loop is equivalent to the condition that each of the indices occurs exactly twice, and this is the case here. And as you can see, these 4 qubits are now local on the chip, so we can implement this 4-body interaction that I showed you before locally, and we do not need long-range interaction. We can now continue this procedure to build up the whole LHZ architecture, and now we have n minus k plus 1 even constraints, so we fulfill the condition that the degrees of freedoms are reduced. All right, so let me give a short summary on that first part of my talk. So what the LHZ architecture is about is to start from some Ising Hamiltonian, which is likely to represent some NP-hard optimization problem. However, it requires these long-range interaction terms, which are difficult to implement. Therefore, we do this LHZ mapping, which enlarges the number of qubits quadratically, but therefore enables us to implement the whole problem only into the local fields. So this is also one of the main advantages, that the whole information about the optimization problems is now stored in these single qubit terms and in local fields, plus this constraint term, which contains of 4 and 3-body interaction terms, which, note that because it's important, are purely local and not long-range things. And in order to do that, we use this parity mapping that maps parallel alignment to eigenvalue 1 and anti-parallel alignment to eigenvalue minus 1, which corresponds to spin down. Right. One more thing that we need now for establishing the universal gate set is that we add this bottom row at the LHZ triangle of so-called data qubits. So what we had before was this triangle represented by the gray qubits. We refer to them as parity qubits, and we add this layer of data qubits, which basically represent the magnetization of the logical qubits. Also, we identify so-called logical lines, which store the information about one single logical qubit. So, for example, this green yellowish line on the very left involves the logical index 0. So all parity information about qubit 0 is distributed among these 5 qubits on the very left. Similar things hold for the other qubits. For example, for qubit 3, the parity information is stored along this line. And these logical lines are now important when we want to apply a bit flip on a logical qubit. Because if I bit flip one logical qubit, then also the relative alignment to all other logical qubits changes. And because the parity qubits precisely encode this relative alignment, we also have to flip all parity qubits which involve the respective logical qubit. And therefore, flipping a logical qubit corresponds to flipping all physical qubits along its logical line. A phase flip, on the other hand, does not change the relative alignment to others, and therefore it is enough if I just flip the phase on the data qubit. And now if I don't want to do bit flips, but more general rotations around the x-axis, I can use this kind of gate circuit. So I can basically disentangle all these qubits by applying this chain of CNOT gates, then doing the rotation locally on the data qubits, and then entangle the qubits again. So for example, for qubit 2, this would be a CNOT gate here, then a CNOT gate here, CNOT gate here, CNOT gate. Can you actually see my mouse?
Yes.
Yes. Okay, great. CNOT gate here, then doing the rotation, and all these CNOT gates are back. So it's basically mirrored, as you can see in this circuit. Right. With that, we actually have now the framework to go into setting up a universal gate set. But I still want to stop once more and ask for questions if there are some.
So those operations that you mentioned was already introduced in this LHZ paper, right?
No. In the original LHC paper, this was purely developed for quantum annealing,
Okay.
where they did not have any gate-based things.
Okay.
But these logical lines, so it's not new that these logical lines exist. We just got them a naming. We also had them in a paper last year, where we introduced some kind of modular QAOA in the LHZ architecture.
Mm-hmm.
And there was also a paper on quantum annealing by Rochetto and some people around him who also already exploited these logical lines.
Mm-hmm. So this operation was introduced by you. Am I correct?
I'm not sure, to be honest. So we actually, yeah, we found it, and we gave it the name a logical line.
Mm-hmm.
But this concept of the logical lines was known before. However,
Okay.
I don't think that this kind of operation was used.
Okay. Okay. See. Okay. Thank you.
You're welcome. Okay, then let's go on. So for a universal gate set, and this is now really what we did in our paper, which was published recently. What do we need? So what we need to establish a universal gate set is we need to be able to do all operations on a single qubit. Plus, we have to have some kind of 2-qubit entangling gate. And if we now wrap up what we saw previously, we know that we have our x rotations in the logical frame and also our z rotations. And because these are rotations, arbitrary rotations about non-parallel axes, we can by using Euler angles, we can construct any arbitrary rotation on the single qubit block sphere. So we can basically do any arbitrary operation on a single qubit. As you can see here, Z rotation in the LHZ scheme is very simple. It's just a single qubit rotations, whereas rotations about this x-axis require these CNOT chains along the logical lines. So what we still need now is some 2-qubit entangling gate, and this is what we are going to look into now. Right. And what it turned out, is that in this LHC mapping, we can implement single body operations only. And this is possible because we have single qubits that already encode the interaction between two logical qubits. So now it gets a bit into math. It's not that important to understand every step here. I just want to show that for completeness. So for example, the rotation, so the single qubit rotation on qubit, so on parity qubit ij, basically corresponds to this exponential, and if I map to logical qubits, this corresponds to this exponential, because the parity qubit corresponds to the product of these logical operators. And if I write that out as a matrix, we have this form of the exponents plus minus I alpha over 2. And what we want to have now is this C phase gate, which has basically applies a phase if both qubits are in excited state. And what we also can use is to use local RC rotations on the data qubits, which so the C rotation on a single qubit looks like that. And if we want to do that on a system, we just tensor product that with the identity and then apply it on the respective qubit. So what we do now is we use this single qubit RC rotation on the second logical qubit and on the first logical qubit. And in the middle, we apply this C rotation on the parity qubit, which in the logical frame corresponds to this matrix here. And if we multiply that, we get this matrix, and we can now arbitrarily choose alpha, beta, and gamma. And if we choose them to be phi over 2, which can be easily found by solving this system of equations, we find that this is up to a global phase equivalent to this C phase gate, which can be executed at any arbitrary angle phi. And if we choose this angle phi to be exactly pi, we obtain the CZ gate, so the controlled phase flip. And with these 3 gates, which we have found now, we have found a universal gate set, which means that we can apply any arbitrary operation in our framework. And yeah, the full universal gate set looks now like that. So we have this logical Rx rotation. Note now that the tilde on the operator denotes a logical operation. So this corresponds to this product of sigma x operations. Basically, this operator just corresponds to this CNOT chain along logical lines. Then a logical RC rotation is basically just the same as a logical, as a physical C rotation on the respective data qubit. And the C phase gate is now decomposed into 3 gates, namely a rotation on the logical qubit I, on the logical qubit J, and on the, so let's say not logical qubit, but data qubit I, data qubit J, and on the parity qubit encoding the parity between qubits I and J. And yeah, what is particularly interesting now is that the C phase gate, which is a complicated 2-qubit gate in standard approaches, can now be implemented by using single body rotations only. And what is also crucial is that we do not need any non-local connectivity. So there are no swapping operation required for any operations in the LHZ architecture. However, we do need these CNOT chains along these logical lines, which, however, only need nearest neighbor connectivity. And yeah, by gate commutation rules, we can basically apply any single qubit operation by squeezing it into in between these CNOT chains, because we can decompose any rotations into a product of x and z rotations. The x rotations have to be in between these chains anyway, and the z rotations will just commute through the control knobs of the CNOT gates. Right. So to sum up, maybe this table, which is also the figure 1 of our paper. So basically the upper part we have seen before. The single qubit rotation are about x-axis translate to these logical lines. A z rotation on a logical qubit also stays a single qubit rotation in the LHZ frame. And the z phase gate, and this is now the crucial point, this is complicated before, potentially requires swap gates, which are here represented by these triple blue lines. And now this is very simple, just parallel rotations on 3 independent physical qubits. One thing to note is that we basically have now shifted complexity to somewhere else. So before the mapping, the z phase gate was difficult to implement. This is easy now. But on the other hand, the x rotation was easy before and is more complicated now. Right. So before we go into applications of that, are there any questions?
I think perhaps we're good.
Yeah, I'm good. Thank you.
Okay, cool. Then, yeah, you will ask, and this question is very much justified. Why do you do this, and what advantage does it give you? And I can tell you that one algorithm where it brings advantage is a very important algorithm. It's basically the basis of many well-known quantum algorithms, such as quantum phase estimation, Shor's algorithm, and so on. And this is the quantum Fourier transform. We published this example and some others in the companion paper of the main paper presenting this universal framework in Fourier FA, and this appeared together with the other paper. So let's now look into this QFT circuit. So the QFT circuit looks like that, and it has this quadratic amount of conditional rotations. And these conditional rotations are basically the same as controlled phase gates. And note, these phase gates can be implemented very efficiently. However, these Hadamard gates are non-diagonal in the C basis. That is, they include a term that corresponds to our X rotations and is therefore difficult to implement. So we can now study this circuit down here a bit. So this circuit is actually the quantum Fourier transform in the parity frame. And what you can here see that the circuit is mainly made up of these CNOT chains. And these CNOT chains come from the implementation of the Hadamard gates. As I mentioned before, logical single qubit gates that are non-diagonal can be realized by squeezing them into these CNOT chains, and this is exactly what happens here. And all the C rotations of the Hadamard and also of this conditional phase gates, these are all executed more or less in parallel. You can find some of them in the circuit. But so the crucial thing that makes up the depth of this circuit is these CNOT chains. And if you cleverly arrange that, I don't want to go into detail here, you basically end up with a circuit depth of 8n minus 9 and a gate count of 2n times n minus 1. And what is interesting now, that on other approaches that implement the QFT on a square lattice, you need 10n minus 13 steps, which is basically 2n more than we do. However, we need a bit more CNOT gates because we have 2n n minus 1 and they have 3n n minus 1 over 2. One fun fact about that, the most efficient known circuit for QFT on an all-to-all connected device is basically is 8n minus 10, and we have 8n minus 9 on a square lattice implementation. So we are nearly as good as QFT on an all-to-all connected device in terms of circuit depth. And I can promise you we did everything to find this single gate to be really as good as that. But unfortunately we didn't manage so far. And just as a fun fact. Right. Another circuit where the advantage of the LHZ mapping becomes even clearer is the quantum addition. Draper developed some quantum addition algorithm based on the QFT in the year 2000, and we picked it up to demonstrate the advantage of the LHZ architecture here. So what you can see here is that this is just again a product of conditional rotations and 2 QFT circuits, which we already know from before. And what we basically do is we add 2 registers A and B. For that, we have to basically add another LHZ triangle for the register B, and then another triangle which is top down here for representing the interactions so the interregister connectivity. And with that, we can implement all this middle part in between the quantum Fourier transforms in a single time step, because all these conditional rotations transform to single qubit operations. So usually this has logarithmic depth, and we do it in a single time step. And together with these quantum Fourier transformation steps here, we end up in linear depth again. Right. Are there any questions on the applications? Or also to earlier slides?
I think not. You can continue.
Okay, cool. Then let me go a bit into encoding and decoding, because in order to make use of all these things, we of course have to be able to encode quantum information in this LHZ scheme. And how this is done is basically displayed on the left here. So let's, for example, consider the initial situation where all parity information is just encoded in the data qubits at the very bottom of the LHZ triangle. And to build up a parity qubit in the first row now, we can basically just apply CNOT gates between qubit I and qubit J and the qubit that shall later represent the parity qubit between them. So in this circuit here, you can see we do a CNOT gate from A to IJ, from J to IJ, and then this red qubit encodes the respective parity. And a similar circuit can be set up for establishing new parity qubits if we have already 3 qubits which form such a parity constraint. And as you can see, these gates are always within such a parity constraint which we constructed before. And if we cleverly arrange that circuit, apply some gate commutation and cancellation rules, we basically end up with a circuit that does the whole encoding in n+1 time steps. So for example, down here, each time step with the same color, or each gate with the same color, can be executed at the same time. And each arrow corresponds to a C0 gate. And we basically build up this whole LHZ triangle from bottom to top, where we worked out which gate can be executed in parallel. Right. I think that's basically it about this. We are maybe just as a side note, we are currently working on a more efficient approach on that, but unfortunately, this is still in the process of patent filing, which is why I cannot yet talk about that. But yeah, this should be out soon. So if you have any questions on that, feel free to reach out maybe next year or so. Right, and then at the very end, maybe just a very short remark on fault tolerance. So what I told you in the very beginning is that we have much more physical qubits than logical qubits, actually quadratically more. And therefore, we have a redundant encoding of information, and we can use this redundant encoding and this redundant information to allow for a bit flip error detection on the one hand, and also correction on the other hand. So if we recall these constraints, which are here shown as a square plaquette, we can now, so we know that the number of spin downs on such a constraint must be even. This is due to these closed loop constraints I showed in the beginning. And we can now check if this constraint is fulfilled by putting an ancilla in the middle of the constraint, applying collecting parity on this ancilla via C0 gates to a Z measurement. And if the outcome is eigenvalue +1, I know the constraint is fulfilled, everything is fine. However, if I get measurement outcome -1, I know that something happened and I have to correct. So for example, down here, we have 9 constraints, which we all measure. And for example, now we get that the 3 constraints where the qubit in the middle is striped, these have now measurement outcome -1. And what we can conclude on that, or from that, is that probably this physical qubit has experienced an unwanted bit flip, because that bit flip would violate these 4 constraints at once. And what we can do then is just apply an artificial bit flip to this parity qubit, and therefore we have corrected the error. Of course, this is not guaranteed that this is doing the correct thing, because this is only the most likely scenario for this syndrome to occur. There may be other scenarios and do probability estimations and correct for the error that is most probable to occur. And we did also some analytics there, and we found that for increasing system size, the probability for experiencing a logical bit flip decreases exponentially with the system size. So we chose here the 2-qubit error rate is equal to the measurement error rate, equal to the initialization error rate, equal to 0.3, and we varied the single qubit error rate among different values. Of course, if it's larger than 0.5, the logical error rate diverges, and otherwise it goes to 0 exponentially. Please note that we did not take into account phase flip errors here, because in the parity architecture as such, it is impossible to correct for phase flips, because a phase flip operation actually is a valid gate operation within our universal framework. But we are working on that, and working on doing code concatenation and things like that to also correct for bit flips, phase flips. Sorry. Right, with that, I'm already at the end. Just to wrap up, we presented a universal gate set in the parity architecture, which allows for a simple implementation of C-phase gates. It has some very important applications, which I showed you. We are also, currently working on a more efficient encoding and decoding approach. We have intrinsic bit flip error robustness. We are also investigating the use of noise biased qubits, which may be interesting because we can only correct for one type of error, and noise biased qubits may be able to be more resistant against the other errors. And yeah, the main challenge at the moment is the missing tolerance against phase flips errors. And yeah, maybe at the very end, I also want to give credits to the teams which I am working with. So I am an employee at Parity Quantum Computing on the one hand side, where I'm working as a quantum software engineer. And on the other hand, I'm doing my PhD with Wolfgang Lechner at the Quantum Optimization Group in Innsbruck. My supervisor, Wolfgang Lechner, told me to announce that he has free PhD and postdoc positions. So if you know anyone, please feel free to forward his email and outreach. And also we in the company are always looking for new people, and are happy if you could forward our email. Yeah, with that, I'm at the end. I want to thank you very much again. And I'm still open for questions for the last 10 minutes.
Yeah, thank you. Yeah, thank you very much for your presentation. It was really nice. And I think we have time for some questions. Does the audience have questions for him?
So I have one question. So when you in this section that you presented encoding and decoding, what I probably missed, what is the task here?
Sorry, maybe I was not clear enough on that. So in order to operate parity qubits,
I think
so what you
we
have
missed
usually
you
at the very beginning. Pardon?
Hi, Michael. I think we missed you for a second. Could you restart again?
Yes, sorry.
Thank you.
So usually at the very beginning of a quantum algorithm, you only have your information stored in these data qubits.
I see.
But in order to apply all these operations in the LHZ architecture, we need the information distributed and angled among all these parity qubits. And this decoding, this encoding procedure allows to build that entanglement up. And on the other hand, at the very end, to read out, I will have to collapse the whole thing and decode again. Decoding might also be necessary if I want to do algorithms that are more efficient in the non-parity encoded frame.
Okay. So could I understand that your encoding procedure is to kind of like construct a fully entangled state?
Yes.
Among those lines.
Yes.
Okay.
The encoding basically entangles all the parity qubits with the data qubits. Yes.
I see. Okay. So My other question would be, so you presented a scheme for bit flip error, right? So basically, if you could perform a Hardeman, right? So you could always convert a phase flip to the bit flip. So there might be.
Yes, of course I can put the Hadamard on all qubits, but then this Hadamard operation will not be error protected.
Oh, okay.
And that's the problem with that. We already also thought about maybe combining two LHC triangles where one is basically Hadamard on all qubits, so we have that in the other bases. But yeah, this is still work in progress, and there arise some difficulty. But yeah, you're totally right. This was also the first thing we thought about. Yeah.
Okay. Okay, that's good from me.
Okay. I have, it's not exactly a question, but could you expand a little bit more on the quantum Fourier transform part? Because,
sure.
Yeah, you went back and yeah, you talk about the depth that was required of 8n minus 9. And later on, you told that you could do this in a single time step, as opposed to, or best
yes,
algorithms that could do
sorry, this is a misunderstanding. I said for the quantum addition, we can implement this part in the middle here in a single time step.
Okay.
But this part in the middle does not contain any Hadamard gates. And the difficult thing in the LHC here are the Hadamard gates because they are non-diagonal. And this linear circuit depth comes from this Hadamard gates. And because the Fourier transform is linear, also, these Fourier transforms will have linear depth. The only thing I wanted to emphasize there at this is this middle step here can be done in a single time step.
Oh, okay. All right. Thank you.
You're welcome.
I think perhaps they're all the questions that we have for now.
Okay.
So I wanted to thank you again for the very nice talk.
Yeah, you're very welcome. It was a pleasure to be here. And
interesting talk. Thank you.
Yeah. So if anything occurs, any questions, any inquiries, please feel free to reach out at any time.
Yes, sure. And as a corporate research center, we also interested in collaborations. So if Parity Q, right, is interested in, we have several directions that we are pursuing. Of course, that at this moment we are working on finding applications that we could demonstrate quantum advantage. So basically, we are looking for quantum simulations,